that's just a clicker question for today. I want to talk about getting back to physics. We're now in our target. We're in our target zone. We're flying over the target. The target is the periodic table, and today we're putting in the concepts that we need. We're going to start by talking about neon. Now, if you've been out driving at night, you've seen a zillion neon signs like this one. All right, and neon signs. You know, this one's the reddish orangish part is the neon. The bluish part is, I don't know what that is, maybe nitrogen or something. But the reddish orange color, this is a pure neon filled gas tube. And it's, you know, we're going to be doing some demonstrations and observations on Thursday of neon and hydrogen. And so if you put a glass tube, you fill it with pure neon gas, and then you zap it with some high voltage, it'll emit this distinctive color, kind of orangey red. Now, here's what we want to tackle today. And everybody's seen neon lights of that kind. If you put that light through a spectrum, it'll split up into its colors. And this is what it looks like. Okay? This is the visible, and we call this a discrete spectrum. D-I-S-C-R-E-T-E. Discrete. In other words, it's not continuous. It's not all the colors of the rainbow. There's a lot of colors on here. And you can see most of them are down here in the reds, yellows, and oranges. Okay? But there's a little bit of blue in there, some green. You know. Now, sunlight, if you put it through a prism or a diffraction grating, you'll get a rainbow. You'll get all the colors of the rainbow, as the saying goes, right? But if you have pure neon under high voltage like this, it will produce only specific colors. You can count them. Okay, there's a lot of them, but they can be counted. You know, with a precise spectrograph is what we call that. And it is not continuous like a you know, if you were to look at one of the incandescent lights in this room, you know, through a prism, you'd see a rainbow, okay? And or a diffraction grating, you see a rainbow on the left, you see one on the right. But with neon, you won't. And I'll bring those in on Thursday, at least one or two tubes, hydrogen and neon for sure. And you can see it with a diffraction grating. It looks pretty cool. Now, this is what we call discrete. In other words, it's countable. It's not continuous, right? Like the rainbow. Sunlight, rainbow. Incandescent light, rainbow. Pure neon, discrete, like this. And now, if you look, so that's neon. Now, if you look at any element, hydrogen, helium, oxygen, neon, iron, they're all here. You can see that they have different spectral lines. That's what we call these, because we produce this spectrum, the discrete spectrum, by shining light through a diffraction grating. And the openings in the diffraction grating are it's like the bars on a jail, the door to a jail cell. You know, they're vertically aligned like that, so the light going through makes vertical linear images like this. So we call them spectral lines. You can see hydrogen up there at the top. That's the one that we're going to study today. But helium, that's right below it. Oxygen, neon, which we already looked at. And there's iron. And you can do this for all the elements. Also, if you have infrared optics, you can spot lines further to the right in the infrared. And if you have ultraviolet optics, you can spot lines further to the left over here past the violet end. Okay, so, but this is the visible, this is the Roy G. Biv discrete spectrum, or discrete spectra of all these elements here. Now, here's what hydrogen looks like. This is what a hydrogen lamp looks like to the naked eye. It's kind of pinkish, almost a reddish, pinkish color. And make a note to yourself, I have some videos in the physical science 1121 area that are labeled. There's a playlist called diffraction, and I have several videos of that. Now they're not as good as this, and they're not as precise as this, but you can see the various spectral lines of hydrogen. So this is the naked eye image. All right, this is what you see with your eyeball. If you put it through a prism or diffraction grating, this is what hydrogen looks like. All right, now I want you to kind of make a sketch here, and instead of sketching in you don't have colored pens, but you can write down, you know, like for this one, red. And then for this one, kind of aqua, greenish aqua. Okay, it's kind of between the blues and the greens, so it's kind of an aqua-ish color. And then down here, let me turn off. No, you can see it. Down here, there's a couple purpley blue lines. Now Thursday, we'll see those. And we can get this room really dark and nice, and you'll be able to see those. There's actually 2 of them down there. Okay, they're really close together. And those are the 4 specific discrete spectral lines of hydrogen. Now they all have names. This reddish one is famous H alpha, hydrogen alpha. And this aqua one, H beta, or hydrogen beta. And then down here, there's 2 of them, H gamma and H delta, to signify, you know, the fact that we've got 2 down there. And you'll see them on Thursday. But these specific spectral lines, they're like the quantum fingerprints of hydrogen. When we see a star emitting a lot of these 4 colors, or 3 out of these 4, you know, because sometimes not all of them are emitted at certain temperatures, you know. But if you see the surface of a star emitting a lot of this stuff, you can say to yourself, "Yep, we've got a lot of hydrogen." And guess what? Most of the universe is most of the visible universe is this stuff, hydrogen. We see a lot of H alpha, H beta, H gamma, H delta, and there's ultraviolet off the left end over here, and there's infrared. I think hydrogen's got some infrared as well off the right end. All right, so we can see those in the infrared telescopes and the ultraviolet telescopes. All right, and those are like the quantum fingerprints. And what they do is they actually encode or reveal to us, now that we know the principles of electrical potential energy, they allow us to figure out how tightly bound an electron is to the nucleus of hydrogen, which is just a single proton. And that is important because the binding of electrons controls all of the periodic table and all of chemistry. Okay, now let's take a look at some of the specs. Now here's a table of wavelengths and frequencies. 656 nanometers, yeah, we've already done that. We did that a couple weeks ago when we calculated frequency from a 656 red beam of light, the H alpha. The aqua line is H beta, and that's about 486. And so what we do is, you know, we put it through like a prism or diffraction grating in the lab, and then we measure the angles, you know, because it won't go straight through. The reds will be off to a certain angle, and then the purples off to a certain angle. We measure those angles. We measure distances to the screen where we're observing it, do a little bit of trig, and we can figure out the wavelength. It's not too bodacious. And then here's the 2 purpley blues, H gamma and H delta, 434 and 410. 410 we did, I think we did that on homework. Or maybe, I think we did a clicker question with 410 nanometers. And we figured out 732. All right. So that's just a, thing, a list of the, some of the properties of the discrete visible spectra of hydrogen. Now there's a fancy name for this series of colors, these 4 colors. These are known as the Balmer series. Let me spell that for you. B-A-L-M-E-R. And it's named after the guy that figured out the pattern in wavelengths. All right. So this question, why isn't the hydrogen lamp like a hot light bulb? A hot light bulb, continuous spectrum. Pure hydrogen, in a glass tube and then zapped with high voltage, only these four colors in the visible. So why don't we get a continuous rainbow? Why only these colors? And basically that's like saying, is there a pattern of any kind in the wavelength or frequency? Now, if you look at those wavelengths and frequencies, you know, you don't have frequency doubling. You know, so it's 457 and then 617 terahertz and 691. You know, you're not really getting, you know, like, or multiply by 3 or divide by 3. You're not getting anything like that. Same thing with wavelengths. The wavelengths are not getting, they're getting smaller, but they're not getting smaller like, you know, 1/2, 1/4, 1/8, nothing like that. All right, so we you know, it's a difficult pattern. The guy that figured it out is named Joseph Balmer, Balmer. And here's the pattern that he found. It's a pattern in the inverse wavelength. So 1/lambda obeys this property. Now, R is called the Rydberg constant, and I'll give you the spelling for that and the value of it in a second. But Joseph Balmer was working with this thing, and he, for some reason, you know, this is back in the 1800s, before Einstein, before Planck, before all these guys, and he worked it out mathematically. You know, he checked lambdas, he checked frequencies. Then I guess he decided, let me check inverse wavelength. So he did all the 1/lambdas, and then he found this pattern that if you take 1/4 and subtract 1/n for these values of n, 3, 4, 5, and 6, you'll get the inverse wavelength of H alpha, H beta, H gamma, H delta. Okay, and you know, so here's the pattern. Okay, there it is. That's the Balmer formula. R is called the Rydberg constant. There's a spelling for it. For hydrogen, its value is 1.097 times 10 to the 7, and then meters to the -1. That means that's the same as inverse meters. Okay, and that's because this is a wavelength of inverse meter. It's a formula of inverse meters. And the Balmer formula says if you want 1/lambda, use 1.097 times 10 to the 7 inverse meters, and then multiply it by the square brackets. Now figure out your square brackets, and we're going to do this in a second. Okay, we'll do n equals 6 together. All right. So that's the formula, and hydrogen, different elements, not all elements obey this, but hydrogen does. There are certain elements that approximately obey it, and they have their own Rydberg constant. But for hydrogen, it's 1.097. And I have a famous problem with this kind of a calculation, but for an element that is called Chucktanium, discovered by Chuck Norris. So you'll see that in homework maybe. And it's a similar Rydberg or a similar Balmer formula. Now let's do n equals 6. All right, so what you do with n equals 6, and this is going to give us H delta, the wavelength of H delta. You put in 1/6 where it says n. So you put in 1/6 squared, and you put in your Rydberg constant. Okay. So here, there's the first line of this equation block, your Rydberg constant, and then in square brackets, 1/2 to the second, that's 1/4. And let me get my cursor over here. Okay. So here's 1/6 squared. All right. So this is doing the n equals 6 level of that table. This is H delta. All right. And then at this point, if you're doing it on paper, if you're doing it on a calculator and you know how to do fractions, you can do it without too much trouble. But if you're doing it on paper, you got to go to common denominators. So common denominators for 4th and 9th fractions, no, 4th and 36th fractions is 36. So 1/4 is the same as 9/36. So that's this one here. First item in the square brackets on the third, or on the middle equation. And then 1/36, we haven't changed that one. Okay. So now now that we have common denominators over here, we can go 9 minus 1, and that gives me 8. And so 8/36. Now you could reduce that to 2/9. Or you can just, leave it there and calculate. And when you calculate, so you could go 8 times 1.097 EE7, and then divide by 36, and you'll get this number, 2.438, I should say, times 10 to the 6 inverse meters. Okay. Now we're gonna turn that into that's 1 over lambda, right? So we're not done yet. We're gonna flip flop it to get lambda itself. But let me pause for questions here. Raise your hand if you have a question at any step. I don't want to leave anybody in the dust. Because I know all kinds of people love so you love fractions? Yeah. Okay. But you still have a question, right? Go ahead. It's Diana, right? Okay. Finally, I learned some more names. Yeah, I just mentioned that. How would you do it in your calculator? 1.097 EE7, and then times 8, and then divide by 36. Or do 8 over 36 equals, and then multiply by 1.097 EE7. You know. So just mess around with it. See the way that you like to do it. You might have to do a Balmer series calculation on the final. I'm not saying what's going to be on the final, but I'm just saying. It goes without saying. Okay. All right. Any other questions? All right. I don't want to put too much pressure on you because this is getting into scientific. Yeah, this is getting into nuclear physics now. So go ahead. $2.438. I'm just using scientific notation. That's the same as 2,340,438,000, which is what you got, right? Yeah, so you're good. Yeah. What you have, you're in floating. If you convert your thing over to scientific, it'll work out that way. Come up after lecture if we have a few minutes, and I'll show you how to deal with it. Yeah, yeah. Okay. All right, now we got to flip-flop that. If we want to get lambda itself, and put that in the table, we got to flip-flop that. So now on most calculators, there's a 1 over button. Sometimes it says x to the minus 1, right? And it might be a second button, all right? So you flip-flop that. So here's what you got, and you flip-flop that. That's like going 1 over 2.438 times 10 to the 6 meters to the minus 1. So now your answer is going to be in a, point four, 4 or point, yeah, 0.4 times 10 to the minus 6. So we gotta do a little bit of work here. Here's what if you do it on your calculator, it comes out looking like that. All right, now we want to move the decimal point. We're gonna try to get nanometers here. Okay, so let's see if we can move this thing over 9 places. Okay, so we'll move our decimal point over 9 places, and that works out to 410.2 nanometers, and that's H delta. Okay. Now let me pause for questions here. Are you good? Okay. All right. Now I highly recommend, let me repeat, I highly recommend that you get facility and get some skills with scientific notation on a calculator, not on the cell phone. On a cell phone you can practice with, but you got to know how to do it on your calculator because you can't use a cell phone on the final. So here's kind of a wrap on the Balmer series. The observable regularity of the Balmer series must indicate some unseen regularity in the atom itself. And that concept, my wonderful students, cannot be overemphasized. The fact that there's a numerical pattern, that's like Galileo's conviction that the world, the universe is an open book and that it's a book written in a language of mathematics. So Balmer figured out one of the mathematical sentences of the universe. And so that must correspond to some F equals MA or, some kind of EPE question or rule, all right? And that's what we're going to try to tackle today. Now, before we take off from that, here's what the sun spectrum looks like. And these little gaps that you see in the rainbow, they symbolize for the sun is incandescent, so it produces a rainbow. The atmosphere above the sun, however, will absorb certain colors. And so the hydrogen atoms floating around in the atmosphere above the sun, they'll absorb a lot of, like this big red gap down here. This might be H alpha down here. I'm not sure, but it might be H alpha. Those hydrogen atoms up in the atmosphere will absorb that. The H alpha color coming off the sun as part of the rainbow. The other reds will go buzzing right past, but that one will get absorbed. Okay, and I'll show you why atoms absorb colors of light. So these are what we call absorption features. Absorption features. In other words, places where a color is missing. And these are equivalent to fingerprints as well. So if we see a star spectrum and we see H alpha, H beta, and H gamma missing, we know, okay, that star's got a lot of hydrogen. Okay, it's hot. It's producing a continuous spectrum because it's incandescent. But it's also got some atomic hydrogen floating around, and those will be the fingerprints of it. Now, here's a picture of a very famous nebula out in the universe called the Rosette Nebula. And this is using a filter for 656 nanometer red light. And so this is what the Rosette Nebula looks like if you only look through a filter for that color. Okay, it filters out all the other colors. But there's other colors out there, and there's other substances out there. And the Rosette Nebula, actually, here's a false color image. Now this one is, it measures, what they did here was, they measured the spectral lines of sulfur. Sulfur's got its own spectral lines. And then they false colored that red. So the reddish parts here are from sulfur. Oxygen, the greenish areas that you can see here, and oxygen, I don't think oxygen comes through as green to the eye. But they used an oxygen filter and then false colored it green. And then the H alpha filter, they false colored that blue. So that's the Rosette. So we use this as a tool. We identify stuff, even in some distant nebula, millions of light years away. And we can see this thing. And here's another nebula. This is a famous one, the supernova remnant in Taurus. And this is in H alpha. And so what we're going to do now is talk about the quantum theory of the hydrogen atom. And, this one, this is a supernova remnant. In other words, it's a large star, many times larger than the sun, that eventually it burns brightly, burns quickly, and then reaches the end of its lifetime and then blows itself up in a supernova detonation. And these are the smithereens flying outward from the detonation. And it's a lot of hydrogen. It's still hot, so it's emitting. Anyway, so let's look at hydrogen. Here's a simplified view of hydrogen. Now, I mentioned that the different colors, H alpha, H beta, and so on, reveal to us the energy levels of the hydrogen atom. And we're basically talking about EPE. So the theory is that because there's a few colors, only a few orbits are allowed, all right? And the electron only lives at certain altitudes, certain orbits, and no others. And that's why we don't have a rainbow. We only have a discrete spectrum. all right? And each altitude has a set electrical potential energy, right? So the discrete means we have a set of orbits, and you can count them, starting with the lowest level, n equals 1, n equals 2, n equals 3, n equals 4, and on up. All right, so countable energy levels. And so this is what we call the Bohr model of the hydrogen atom, discovered by or developed by Niels Bohr from Denmark. And Albert Einstein added some finishing touches to it. Okay, so for instance, so there's my energy levels. So if you look at n equals 3 and n equals 2, you know, n equals 3 is going to be a lot of potential energy, and n equals 2 a little bit less. Okay, but instead of converting to kinetic energy, what happens is it emits a photon. So the electron emits a photon as it deorbits. So from n equals 3 down to n equals 2, they worked it out. That's the H alpha. When an electron goes from the third energy level down to the second, that's just the right energy for an H alpha photon. And just the right wavelength, just the right color for the H alpha. So this little transition here from n equals 3 down to n equals 2, and bang, a red H alpha photon is emitted. All right? And now your electron's down there at n equals 2, and guess what? If there's an H alpha incoming, it can bump the electron back up to n equals 3. Go ahead and make a note of that. The reverse process is also possible. If you get a red H alpha in, it'll bump that electron from n equals 2 up to n equals 3. Nice. And now when it decides to drop back down, electrons always want to drop back down to the lowest energy level. They'd like to get down to n equals 1. And so you bump it up with an incoming H alpha, and a short time later it'll zip down, it'll deorbit to n equals 2, and emit another H alpha, a nice red one. All right. Now the guys that figured this out figured, okay, number of the orbits, electron drops down to a lower EPE. The missing energy, the delta EPE, goes into the photon. Now, how does the photon get that energy? Well, the guys that figured that out were Niels Bohr and Albert Einstein. And they figured out the photon energy from the countable quantized atomic energy levels. And here's the formula that Einstein proposed, that the energy of the photon is Planck's constant, h, times the frequency of the photon. So if you think about it, you know, you're looking at, you know, the discrete spectrum of hydrogen, and you say, all right, if I can figure out the frequency, I can figure out the energy, if Einstein is right. So I go into the lab, I measure, do a little bit of trig, some Pythagorean theorem and stuff. You guys, if we had a lab class for this class, which we were supposed to have, you guys could measure hydrogen just like that, just like Niels Bohr and Einstein. It's not hard. You guys, it's really just a bunch of right triangles and stuff to get the wavelength. And then to get the frequency, you C equals lambda F. You know, you figure out the frequency, the wave equation for electromagnetic radiation. And then once you have the frequency, bang, you use the energy formula, E equals HF. And what that tells you, that's the energy of the photon. And what that tells you is the change of electric potential energy for the electron. Right? So Einstein says, yeah, E equals HF for a photon. Everybody knows that. And so let's assume that that's the change in the electrical potential energy for the electron that emits it. Okay, the electron loses so many joules of energy, or so many electron volts of energy. And so that means the outgoing photon has that same amount of energy, and therefore a certain frequency, certain wavelength, certain color. And as I've mentioned before, Planck's constant is essential to this, and this is why I always say, that Planck's constant, the one constant to rule them all, it is involved in every single physical transaction. When you taste something, a strawberry milkshake, you smell something, smoke coming from a campfire. When you see something in your eye, the retina, when you hear something, your nerve impulses going from your eardrum all the way up into your coconut. All those things are ruled by, chemical reactions and physical interactions, and H is in every single one of them. All right? Oh my goodness. That's all I want to say today. We went so. Does anybody want to go back and go over something? Or do you want to dismiss early today? Dismiss early? I usually put 30 slides, and I put in 33 today, and we just went so fast, and it's only 11:19. Okay, I'll give you a short hydrogen homework tonight. In fact, I'll do it right now. And yeah, SI and SI Study Union. And I'll see you tomorrow for office hours, tomorrow morning, if you can make it. Okay, you're dismissed. Wow, a fast lecture for once. If you have any questions about stuff, come on up. You want to check with the calculator?
No, I figured that out.
You got it squared away?
How do we study for the final?
Study for the final? How do you do
How
that?
should we do that?
Study everything, my friend.
Lectures, quizzes, everything?
Study YouTube's. Double check your lectures against YouTube. That's always a good technique. Go over the clicker questions. Go over the homework questions. All right? And because, the clicker questions, well, except the dipsy one I put in today. But most of the time we have a clicker question about a calculation or a concept or something. It's in there because I think it's important. And because it's important, it might be on the final. Same thing with homework. Because I'm not going to, I only have a certain amount of homework I can give you guys without you guys totally, frying your brains. So I only have to give you stuff that's important. So if it's on homework.
Every problem and know everything from the quiz.
Yeah, basically know everything. Yeah. For the first day. Nothing much, just know everything. But I mean, the priority should be lecture. That has priority. And then priority 1.5 is clicking and homework questions. Okay. And then priority number 2 is anything else you can read about any topic that we've had. All right, man. Good.
Hi.
Yeah.
I know we only had one clicker question today, but I left my clicker at home and I took notes on everything. Like I wrote down the clicker question and the answer that I put.
Yeah. But you're here pretty much every day, right?
I've missed I think 3.
Ooh.
Yeah.
Well, see, the thing is, you have to have your clicker with you in class to participate. I mean, that doesn't sound very smart, but I mean, technically.
Yeah.
So, but usually a student has 1 or 2 lectures to burn. So, now I'm gonna